Thank you for the kind introduction. Thank you to all of you for being here. I really appreciate you taking time to spend with me today. So today we're going to talk about PurpleAir sensors, which are a new type of air quality instrumentation to enhance community engagement and data collection in under-monitored areas. So to start, I want you to think about the room that you're sitting in right now. All around you, there are lots of things in the air that you can't see, but you inhale them every time you breathe. And a lot of these things are good and we expect them to be there, like water molecules. But sometimes there are other things in the air that we don't want to be breathing. We typically refer to this as pollution. One context that we should be thinking about where we can have elevated levels of air pollution is next to industrial activity. Additionally, I want us to be thinking about how who you are can correspond with your exposure to air pollution. There's lots of evidence to suggest that both low-income communities and communities of color are more likely to face disproportionate health impacts from elevated pollution levels. Additionally, rural communities are typically outside of the networks that we use to monitor air quality, so issues can go unaddressed in these communities for lack of information. The specific type of pollution that I'm going to talk about in this presentation is called particulate matter. We define particulate matter by its size. So to start, we have PM10, which stands for particulate matter with a diameter of less than 10 micrometers. And we care about PM10 because it reduces visibility. What I mean by this is if you look in the image on the left, you can see really far with a lower concentration of PM10. But then when we have a higher concentration of PM10 on the right, you can't see as far, and so your visibility has been reduced. Even smaller than PM10, we have PM2.5, which stands for particulate matter with a diameter of less than 2.5 micrometers. And these particles really become an issue for health. So on the left, we can see with PM10, the particles are big enough that they only get inhaled into your upper respiratory tract, which means you can cough them out. But with PM2.5, they're so small that they go deep into your lungs and they can start to cause health issues because of this. And as with many types of pollution, the amount of pollution that you're exposed to will correspond with the severity of your health impact. So a way that we can start to correlate the amount of particulate matter with a health impact is with something called the air quality index, or the AQI. So with this, you take a concentration of particulate matter and you convert it into an AQI score, and then specific ranges of the AQI will correspond with specific air quality conditions, ranging from good all the way to hazardous. If you recall, I said we were going to be talking about something called PurpleAir sensors, and this is actually where the name for the PurpleAir sensor comes from, because this designation for very unhealthy air is coded as purple. And PurpleAir sensors are a really important thing to be developing along with other air quality sensors, because particulate matter is actually considered a leading global health concern. In a number of studies, they have found a huge number of people dying every year globally from particulate matter. For example, in this study, with something called the Global Exposure Mortality Model, there was a prediction that approximately 8.9 million deaths occurred in 2015 from long-term exposure to PM. So this is a really serious global issue that we need to be thinking about. And the impact of this particulate matter globally is not distributed equally among who it impacts. So in a study of the population of people in the United States who receive Medicare assistance, this study found that even below the current national standards that the government has set for what is considered a safe level of particulate matter, there were pronounced health impacts, particularly among self-identified racial minorities and people with low income. So that makes particulate matter an environmental justice issue. To address this environmental injustice, communities will need a way to monitor their personal exposure to particulate matter and to enhance access to particulate matter data that they might already have. So if someone was going to think about trying to expand air quality monitoring, the first way you might think about this is to do what we've always done, which is conventional air quality monitoring. But I'm going to argue that there are some weaknesses with conventional air quality monitoring that don't make this the best option for expanding access to data. So these are images of what a conventional air quality monitoring tower might look like. And the first thing I want you to notice is how complex this appears to be. I don't know about you, but even as someone who's had some training in particulate matter monitoring, these instruments are not very accessible. I wouldn't just know how to walk up to them. And typically people need really specialized training, maybe even to the level of having a PhD, to be able to use these instruments in a way where they're doing it autonomously. Additionally, these instruments are really expensive. Even just one of these instruments might cost more than a car, which means it isn't feasible for a community to buy one of these towers and maintain it on their own to be able to monitor air quality. Furthermore, they're stationary. And at first, it might not seem like it's a problem to have a stationary air monitoring device. But if we think about this a little more, our sources of pollution can change with time. So perhaps someone decides to install this sensor at this location because down the road there's a factory that is known to pollute. But in 20 years, perhaps that factory decides to move locations and you're not able to move this tower with it. So because we have changes in our pollution sources, we want to be able to have portable air quality stations. In addition, these stationary sites are sited in a way that leaves some people without air quality data. So this is a map of all the active particulate matter 2.5 stations that the EPA runs around the country. And you'll notice that there are some places that have really dense amounts of towers. For example, California, New York have a lot of these air quality towers. And if you were to zoom in on this map, you would see that certain places within these communities have more towers than others. Additionally, there are some places like Nevada that has pretty much no air quality monitoring. So this leaves Nevada without any important air quality data. The final weakness I want to address for conventional air quality monitoring is that it collects data on a coarse time resolution. So what do I mean by a coarse time resolution? If you were to take a data point for 1 minute, and then you wanted to take a data point for the next 4 minutes to give you 5 minutes of data, maybe that would be considered a fine time resolution. But it might be the case that you're only able to take one data point for that whole 5-minute period. And this means that you're going to miss out on changes to the system that occurred within that 5-minute period. So happily, there's a new type of low-cost air quality sensor that's coming onto the market that can address a lot of these weaknesses of conventional monitoring. For example, this is a sensor called the AirBeam, which is wearable, so it allows people to walk around and monitor their personal exposure while they're outside. This is the Air Quality Egg, which is designed for citizen science and the classroom environment. And here we finally have our PurpleAir sensor. And I want to highlight a characteristic of the PurpleAir sensor that is pretty unique compared to these other low-cost sensors. So one of the really good things about conventional air quality monitoring is that it's designed for long-term outdoor monitoring. You might be able to imagine from looking at these other sensors that they're not really set up to be left outside for weeks or months or maybe even years at a time. But the PurpleAir sensor is actually designed to do this long-term outdoor monitoring. So it is kind of a great bridge between these low-cost air quality sensors while also being able to address a lot of the weaknesses of conventional monitoring. So for this study, we had access to a number of PurpleAir sensors, and I'm going to address the ways that it can address the shortcomings of conventional monitoring. So these sensors are low cost, ranging from $180 to $260. Depending on how many features you want, and that's certainly more affordable than trying to buy an instrument the cost of a car. They're easy to use. I like to think of these sensors as the IKEA of air quality instruments. If you follow the directions, hopefully you will be able to install it. They're portable, as you can see in the image here, so if your pollution source changes, the sensor's location can change as well. They offer enhanced access to data. So this is an open source map that all the data that's collected with PurpleAir sensors in the world goes to. So that means anyone with a Wi-Fi access in the world can access this data. And if you were to click on one of these sensors, you will see that it offers a really user-friendly data visualization option. So as the sensor collects data, it plots it in real time and corresponds it with the AQI index that we talked about. So this gives people a really nice way to get a basic sense of how their air quality is looking without having to download the data and go through a whole analysis process. Okay, so this all sounds great, right? But it sounds a little too good to be true. And there is one weakness with these sensors that we need to address, which is that they have an unknown data quality. So what do I mean with unknown data quality? This basically means that we don't know how trustworthy the data from these new sensors are. And that's a problem. We like to certify air quality instruments in the same way that we like to certify doctors. If you certify a doctor, then you know that they know what they're doing, and you know who doesn't know what they're doing. In the same way, we like to certify air quality instruments so that consumers of these instruments know how good the air quality data is. So although these sensors have not received a formal certification, there is actually a way that we can begin to understand the data quality ourselves. And that's something called a validation study. In a validation study, you'll take a sensor with an unknown data quality, such as your PurpleAir sensor, and then you compare it to a sensor with known data quality. Then you can introduce a source of particulate matter and compare the data collected between these two sources. So we actually conducted a number of validation studies for this project using the PurpleAir sensor compared to something known as the TSI sensor, which is pictured here. And I'm going to walk you through a comparison of these two sensors before I show you a comparison of the data so you can understand how these two sensors differ from each other. In terms of certification, the PurpleAir sensor does not have a formal certification available, but studies to validate these sensors against conventional monitors are starting to emerge. In terms of the TSI sensor, it meets rigorous factory calibration standards that ensure that we know how accurate the measurements are. So we have very trusted data with this sensor. In operation mode, the PurpleAir sensor requires a Wi-Fi connection, and it requires a connection to a power source. So this means that this will limit where we can put a PurpleAir sensor. In comparison, the TSI sensor does not require Wi-Fi, and it can run indefinitely with the power source or on a battery for 10 to 20 hours. And this is great because it means that we can just put the TSI sensor out into a field. We don't need to have an outlet, we don't need to have Wi-Fi, and it can do its thing. With our data resolution, the PurpleAir sensor has a resolution at its finest, which is 1 minute. With the TSI, we can go all the way down to 20 seconds, so that has a finer time resolution. The PurpleAir sensor has 16 gigabytes of data storage available, whereas the TSI sensor only has 0.005 gigabytes, so it requires more consistent data download. And next, for the units with data output, the PurpleAir sensor gives us mass concentration units only, whereas the TSI sensor, we can choose what units we want our data output to be. So this can be either counts, number concentration, or mass concentration. And I know units are not everyone's favorite thing, but as a chem major, they happen to be something that I'm very fond of and they're very important. So we're going to talk a little bit more about these sensors and how to convert them. So if we start with our count, we can get to our number concentration just by knowing the volume of air that went through the sensor for a given period of time. Then we need to make the jump to a mass concentration. And to do this, we need to make two assumptions. First, we have to assume a density. So we've defined particulate matter as being particles that have to do with a particular size. But even if two particles are the same size, they might have a different chemical composition. So for example, particles from a sand mine will have a different chemical composition than particles from a wildfire. So we need to assume a density of the material that makes up the particle. And we need to make an assumption about the shape of the particle. And we typically assume a spherical shape for particulate matter. And this leads us into how the sensors actually collect the data, which differs between the two sensors. With the TSI sensor, we start with an aerosol inlet that is specially designed to channel our particles so that we get to a point where we know that we're only looking at one particle at a given point. When we're looking at that one particle, the way we actually figure out how big it is a laser is shot towards this particle. Light is scattered from it, and then a photodetector will pick up the amount of light that is scattered off of this particle. From there, the amount of light scattered goes into 16 different bins of particle sizes, and from there, we return to our conversion for units, where we go from number into our number concentration. We assume a density in our spherical shape, and we ultimately end up in mass concentration. So what I want you to take away from this is that every step along the way of the TSI sensor, we understand how the sensor is working. We know how the instrument is built, and we know how we're converting from our amount of light scattered into our ultimate units. And this is a really important thing. Unfortunately, this is not the case with the PurpleAir sensor. With the PurpleAir sensor, we know that there's a general mechanism through which the particles are sucked up into the PurpleAir sensor with a fan, but there's no guarantee that the PurpleAir sensor is only sampling one particle at a time. Once the particles are inside of the sensor, we have a general process of light scatter. This light scattering process looks something like we have our laser input, which encounters a particle. Some of that light will not be scattered, while some of it will be scattered and is picked up with a detector. Alternatively, if we had the same laser input, but a larger particle, we would have less of that light not being scattered and more of it being scattered, which would tell us we have a bigger particle. However, once we get to this amount of light scattered with an unknown number of particles, then we kind of lose track of the conversion process. It goes through an unknown proprietary information process to convert all the way into mass concentration. And I'll take a small tangent from this to express, we spent quite a while trying to figure out what this proprietary information actually was, to the point that over the last 3 years, I've sent multiple emails to the PurpleAir company, to the point where I was even emailing with the R&D division of the Japanese company, which makes the laser, to try to figure out this information with no avail. So what this means is that right now we're not comparing apples to apples or oranges to oranges. We know exactly what our mass concentration is for the TSI, but we can't be sure that it's the same type of mass concentration with the PurpleAir. Okay, so I've explained to you how we actually set up our validation process, but let's start to actually look at some of this validation data. So as a reminder, this is our lab setup, and we conducted 4 different validation studies using PurpleAir sensors. One way that we can interpret the validation data is with our R-squared value. So if we're plotting our TSI data against our PurpleAir data, if our data has a really close fit when we do a linear fit, we're going to have an R-squared value close to 1. Alternatively, if our data points are more scattered when we plot the 2 data points against each other, we will see that we have an R-squared value further from 1. So we're going to be looking for an R-squared value close to 1. Okay, so now we actually get to some data. And before I dive into interpreting this, I do want to say we spent a really long time trying to analyze this data in different ways. And I want you to take the conclusions that I'm getting from this data as with a grain of salt. And I want you to think of them as a hint as to new directions that this project could go and things that we should be looking towards understanding better with these sensors. And we have a really small sample size, so by no means am I saying that this is a definitive result from these sensors, but this is where we think we're headed with these sensors. So if we check out our R-squared values, we see that they're really good for our PM1 and our PM2.5 data. So with PM1, we've got an R-squared of 0.96, which is super close to 1. Similarly, for PM2.5, we have an R-squared of 0.97. But if we're being conservative, we notice that our PM10 data has a slightly lower R-squared value. So what this means is that right now, based on the R-squared values, our PM1 and PM2.5 data appear to match with the TSI quite well. However, the PM10 does not appear to match with the TSI as well. Given this, right now we have more reason to trust the PM1 and the PM2.5 measurements as opposed to the PM10 measurements. But again, we're not certain we're actually comparing the same mass concentrations among sensors, so we need to do more work here, and this will allow us to analyze the data in more robust ways in the future. So this is the result that we saw in the lab context, but we have an additional context that we can think about for validating data. And we want to know, do we see a similar validation result in an in situ context? So what I mean by in situ is that we're actually looking at data collected in the natural environment. We happen to have data from monitoring particulate matter emitted by a frac sand mine on the fence line of a Wisconsin farm. The reason that this air quality was being monitored in this location is that frac sand is known to have a number of health impacts, such as silicosis, lung cancer, and a variety of long-term health effects. So in the same period of time, we had 2 PurpleAir sensors installed in this location. So we had a PurpleAir sensor at Adams Farm, which is on the fence line of the mine, and we had a PurpleAir sensor at the background site in a similar region. So what I mean by a background site is a place that is far enough away from the mine that it shouldn't be picking up the particulate matter from the mine, but close enough that it should be having a similar air signature. And we also had the Artemis platform at this farm at the same time. So if you're familiar with Deanna's lab, you'll know about the Artemis platform, or if you caught Carl Painter's talk, you'll know about it. And inside of the Artemis platform, we have housed the TSI sensor for a number of points throughout the years. So we had the TSI sensor at a very similar location to the PurpleAir sensor. This meant that we could take data from our PurpleAir sensor at Adams Farm and the TSI, clean and merge them, and ultimately compare them to make an impromptu validation comparison. So again, we see that PM 2.5 is behaving better than the PM10, and I'm not showing you PM1 here. But with PM 2.5, we have an R-squared value of 0.36, compared to an R-squared value, which is so horrible for our PM10 of 0.0081. So you might be thinking, okay, Elizabeth, 0.36, that's not close to 1. I'm going to argue that for this context, it's actually decent. In the natural environment, we have a lot more complicating factors than when we're in a lab. When you're outside, you have to start thinking about things like wind direction, the amount of sunlight, if it rained, lots of other complicating factors. Additionally, because this was an impromptu comparison, we did not have the opportunity to locate the TSI sensor as close to the PurpleAir sensor as would have been preferred for a validation study. So for having two sensors far apart from each other in a complex system, I think that it's fair for us to use this lower R-squared value and just notice that it's higher than our PM10 value. Another thing that we noticed by analyzing this in situ validation result was that the average of time we use matters. So because we had so much data collected over a long period of time, we were able to play with the average that we had. And you'll notice on the far left, we have our PM 2.5 data in terms of a daily mass concentration. In the middle, we've got an hourly mass concentration. And on the far right, we have a 10-minute average. And you'll also notice that the R-squared value gradually gets worse the closer we get to our 10-minute average. So what this tells us is that our TSI and PurpleAir data are aligning better when we use a larger time average. Finally, I want to address how the PurpleAir sensors are actually working really similarly at this environment. So we know from previous studies that the mine does not seem to be having a severe impact at Adams Farm relative to the background site. So we should expect that the air collected with the two sensors should be similar at the same points in time. And we do actually see this. We have an R-squared value of 0.93 when we compare our PurpleAir at Adams Farm to our PurpleAir at the background site. And this is really exciting because we know that both of these mass concentrations are the same thing. We're definitely comparing apples to apples here. So what this means is that the PurpleAir sensors work well relative to each other, which is great because this project would become even harder if one of the sensors was going rogue relative to the other one. But this means that there might be some amount of consistency among PurpleAir sensors so we can compare relative data between the two. So for now, we're thinking that PurpleAir data is most trustworthy with PM1 or PM 2.5 data and with a larger average such as a daily average. But we need to dig deeper to understand PurpleAir sensors because we see that they're working well relative to each other, but we still don't know how to compare them to the TSI or any other instrument that has unknown data quality. To practice actually using these restraints, we wanted to see if it was possible to collect useful information with the PurpleAir sensors that we had previously used to collect data using these restraints. So if we stay at Adams Farm for a little longer, this is an image of the mine that was taken from the Facebook page of the mine, which I think is kind of ironic because it literally shows at least PM10 being generated here because of the reduced visibility. So here we have some histograms of both frequency and cumulative percentage at Adams Farm and the background site. Our data is color-coded with the air quality index that I discussed earlier, with green being good, yellow being moderate, orange being unhealthy for sensitive groups, and red being unhealthy. And the really good thing is that when we look at this data, we see that the vast majority of days fall into the good or moderate air condition standard. And this is great because the EPA designates that air quality of the good or moderate condition is acceptable. So this means that residents of Adams Farm and at the background site are likely not experiencing health impacts over a majority of days in this region. Another place that we had the PurpleAir sensor was in Dhaka, Bangladesh. So this is Ramisha, and she was a student who helped me collect validation data along with Sadie Hennon. And Ramisha is from Dhaka, so she was willing to take some sensors home with her. And I want to give a big shout out to her for doing this because it turns out that airport security in Bangladesh did not take very kindly to having the PurpleAir sensors as a carry-on. So I want to thank her for her persistence in getting these sensors home. I really appreciate it. So she installed these sensors at her house, and still today, they are the only PurpleAir sensors that are installed in the entire country. And this is a really important place to be monitoring particulate matter because Dhaka is known to have some of the most elevated PM levels in the world, to the extent that studies suspect that people lose years of their lives by living in this place with such elevated PM levels. And when we analyze the data, we do see really elevated PM levels. So here we see that the vast majority of days fall into the category of either unhealthy for sensitive groups or just plain unhealthy. The sensitive groups referred to here refer to elderly people, children, and people with health sensitivities to air quality. Additionally, we see that we get up into the category of very unhealthy with our purple coating here. So this data indicates that some work needs to be done to improve the air quality in Dhaka and to reduce the health impacts that people are likely experiencing from these elevated levels. Next, I want to talk about a vision we have for how we can move forward with these PurpleAir sensors. So we had an idea that we could have an array of PurpleAir sensors that can monitor wildfire emissions in an under-monitored region of Montana. So you might be familiar with hearing about wildfires in places like California, but there are just as many big and devastating fires in other places like Montana. But in Montana, they don't have sufficient infrastructure to monitor the emissions from these wildfires to understand the health impacts. So because we know that our PurpleAir sensors work relative to each other, we had an idea that if we installed a regional array, we might be able to compare data among different PurpleAir sensors whenever a wildfire occurred and get a better understanding of potential health impacts that are occurring. To do this, we took pairs of validated and unvalidated sensors along with necessary supplies such as a power supply, materials to install the sensor, and an installation guide, and we sent them off to family and friends of Deanna's who live in Montana. So one of these sensors got installed with Deanna's brother Chris in Three Forks, and I want to spend a little time talking about the fact that only one of these sensors got put up. So in any given community engagement project, there are two motivations at play. One of those motivations comes from the scientist, and the other motivation comes from the community that's being engaged with. So in terms of my motivation, I was really interested in understanding these sensors because I think that they have value and that they can help people. And we sent them to a place that we thought would be helpful. The community's motivation, on the other hand, is probably more focused on being able to understand when there's a fire if they're experiencing any health impacts. So only one sensor got installed, and probably part of this is that I did not have the time and I didn't put in the time to being really persistent with communicating with the people that we sent these sensors to. And this was a really important lesson for me to learn as a young scientist. A lot of times we put a lot of emphasis on how hard the science is and how hard it was to get the sensors there, but it is just as complicated to engage with a community in a healthy and sustainable way. And I certainly did not have the time to put into this engagement portion of it. So that's one reason that these sensors probably didn't get installed. And if my motivation had been greater to try to understand these sensors and really get them installed, I could have spent time really talking with people and really building relationships, and perhaps they would have gotten up. But that was not the case. To talk about the next element of the community's motivation, what's relevant to understanding this is there were fires in northern Montana in the time that the sensor got put up, but happily, there were actually not any fires in western Montana this year. And we suspect that once there is a fire in Montana, people might be more likely to get those sensors up. And this, I think, is probably a more organic and beneficial process for the community to have it happen in this way, because we don't ever want a community science project to be a burden on the community. And I don't think we talk about that enough in the scientific community. So by having a community be motivated to install the sensors, in addition to pairing it with sustained communication from the scientist, I think that that will probably be the best model for having a sustainable and healthy community engagement project happen. Okay, so this project has been a really empowering experience for me to learn more about these sensors, which I think have important implications for environmental justice. And this has been a good study to start understanding these sensors better so that other people in the future can continue this work and develop a better understanding of this new paradigm of air quality sensors that are available. For future work, we need new and improved validation studies. In this, we will need to be identifying how the PurpleAir is actually getting the mass concentration value. In the lab situation, it's going to be important to have a known continuous source of particles. So for us, we were just literally burning sticks in the basement of Stites in a tiny barbecue, and that's not a very continuous source of particles. And because it wasn't continuous, we also couldn't monitor a given concentration of particles for a very long period of time. So it's going to become a useful thing to have longer periods of monitoring for a given concentration of particles as well. In the in situ context, it will become important that the sensors are ideally located to each other so that the data comparison is a little better. And finally, we are looking for a student to continue the Montana project. So if you happen to know someone who is interested in environmental justice or air quality, or even things like data processing and data analysis, feel free to connect them with either me or Deanna, because I think this is an important and a really cool project that could go in some good directions. For acknowledgements, I want to start by acknowledging the land that this work occurred on. Lawrence University's Appleton campus and the study sites of the Wisconsin project are located on the ancestral homelands of the Menominee Nation. The study site of the Montana project is located on the ancestral homelands of the Salish Kootenai. Currently, there are 11 federally recognized Native American sovereign nations in Wisconsin and 7 federally recognized Native American sovereign nations in Montana. I acknowledge these Indigenous communities who have stewarded this land throughout the generations and pay respect to their elders past and present. And for some personal acknowledgements, I want to start by thanking Deanna. This project would not have been possible without the level of advice and time that you put into it, which I really appreciated because this was a really empowering project for me. But also you have become a really important person in my life in the last 4 years. You're someone that I really value, and I don't think that my Lawrence experience would have been as impactful as it was without you being in my life. So I hope you know how much I appreciate you. I also want to thank all of our PurpleAir hosts. So Helen Adams and Ed Adams, and thank you for being here today. Claire Curvin and Graham Sazama, also thank you for being here. And Chris Donahue for installing the sensor at his home. Also Ramisha and Sadie for helping me collect all the validation data. We were acting like mad scientists in the basement of Stites for a good term there. Thank you to Daniel Martin for assisting in said mad science efforts. Excuse me. And Carl Painter for helping Deanna write the code that we use to convert the TSI data. The Riston Scholarship was what allowed me to purchase the PurpleAir sensors, among other things that have been beneficial for my education. And I want to thank all my family and friends that are watching. I don't think that I would be where I am today without the support network that you all have provided, and it certainly would not have been as fun. And before I move us to questions, I did just want to take one more minute to address something that I know has been on my mind and has been on other people's minds as well recently. In this presentation, I touched on environmental justice, and it is a reality that many Black communities in our country do have additional health impacts that are disproportionate to other communities. And these disproportionate health impacts stem from the white supremacy that this country was founded with and the legacy and continuation of this harmful system today. Similarly, the police brutality that we've been seeing in this country stems from this harmful system. So if you are someone who is looking to be an ally to Black communities, I would invite you to join me in, after this presentation, reaching out to learn about more things to do to support Black communities, such as making donations, joining community groups where we can come together and educate ourselves, making phone calls to politicians and other people in positions of power. And I would invite you to connect with me to do that, because I do think that this is something really important that we should all be working on together. And I didn't feel right having this project presentation where I talk about environmental justice without addressing this at the end. So I appreciate you taking the time to listen to me speak about this. Thank you, and with that, I will take any questions.
Thank you, Elizabeth. There are lots of you, so I am happy to take questions either through raise your hand or raise your hand on the participants page, or just chime in. I will try and page through. You can even chat a question, however you feel most comfortable. I will try and help. Any questions? I guess just shout it out if you do at this point.
Elizabeth, this is Marcia. I'm not on video, but hello, wonderful job. I've been curious if during this time when industrial activity and traffic are way down, if you've been looking at some of the PurpleAir sensor data, and can you pick up lower amounts of PM in the air nationally, locally, globally?
That's a really awesome question. I'll be totally honest, I was really focused on the old data sets that we had already downloaded, but now that you've asked me that question, I'm totally going to look into that after this presentation, because I would suspect that we would have some lower emissions in some places because of that.
Yeah, it seems like the density of those air sensors could really be a valuable data set to look at in the future.
Yeah, I think that's a really good point.
I will add that there are some indications that overall we are seeing a decrease. I think it's a little bit interesting when you start talking about particulate matter itself, that actually might have a positive impact on climate. So it might actually enhance how much warming we have. So it's an interesting relationship there that's also worth exploring. We might actually see more impacts of climate change as we clean up our air, which is interesting.
I have a question. So how come when the company made these PurpleAir sensors, wouldn't they have been doing the validation aspect of it? Like, how come you had to do that?
Yeah, that's a good question. I think possibly part of it was the amount of resources that this company had available to them. Something I've noticed in emailing with them is that there seems to be a really small team of people who developed these sensors and provide the tech support. So it might be that they just didn't have the time to do it. For some perspective, like even for us just doing those 4 validation studies, that took an entire term of us collecting data and coming up with a method for doing that. So it might have just been that they didn't have the capacity to be working on that. And we have a lot of pretty rigorous standards in place for how we certify just general air quality sensors. So I'm not entirely sure, but I think at this point in time, the government standards that we have, the PurpleAir sensor might not have qualified to even be certified specifically. So I think there are some probably systemic barriers to how we are also certifying our air quality sensors that made it less likely for these to be formally certified.
Thank you.
Jana, there's some questions in the chat.
Oh, sorry, I'm having trouble today. I apologize. Will the PurpleAir sensors be continuing as a project at Lawrence?
Yes, so we will hopefully be continuing the Montana project as long as there is enough student support for it. Definitely the Montana project, yeah.
We got one here too.
Hi, Elizabeth. I was wondering if you could talk a little bit about how your experiences in environmental communication impacted the way that you did this presentation.
I think that learning more about how we can effectively communicate science has really reshaped the whole way that I do science, all the way from the lab or my literature searches up to presenting it. So definitely the focus that I have has shifted because I'm more interested in realizing how the science impacts people and trying to make sure that I'm not abstracting science into this academic context that sort of is outside of the real world of impacts, particularly in the context of things like climate change and environmental justice that are really rooted in communities.
That's terrific. And just as a side note, I think you had some effective lessons you must have learned about communication, because the 4-year-old was wrapped through the majority of your presentation.
That's awesome. Thanks.
Other questions? It appears, if I'm missing you, just speak up or chat. And otherwise, I really thank you all for joining us today. If you would like to give Elizabeth one last congratulations. And if you want to stay and ask any questions afterwards, please let me know. I don't know if some of the questions that are coming through late, I think my internet is working very poorly. I did have one more come through, Elizabeth. Are there any additional groups, academic or otherwise, utilizing PurpleAir data to provide studies that support improving air quality of certain affected communities or reducing the impact? So any other studies using PurpleAirs?
Yes. There are actually a number of communities that are starting to use PurpleAir sensors. One really prominent example is Little Village in Chicago, which has been using PurpleAir sensors to monitor PM emissions, which was relevant because they had a coal plant, I think it was, in their community, and I think also diesel emissions from all the trucks that are going through that community. So there are certainly a lot of places that are starting to use PurpleAir sensors, and I've seen other studies that use them for things like monitoring dust coming off of piles of minerals that had been mined and things along those lines. So they're gaining in popularity for sure.
Awesome. I will also just say that we do plan on continuing our work out at Adams Farm to really kind of keep understanding how the sand mine impacts, and we will probably be doing that both through the Artemis platform and the PurpleAir platform as two different accessible points. So not only will the Montana PurpleAir project hopefully continue if someone can join me in that effort, but also the Artemis and PurpleAir projects I hope to continue as well.
Thank you for clarifying that, Deanna.
I hope everybody has a great day. Stay and ask questions. Otherwise, I will see you hopefully tomorrow with our last two talks, or whenever I have an opportunity to see you next.